Welcome to another video in the series about the C7000 compiler. This is the first of two videos which describe the feedback the compiler generates for a software pipelined loop. My name is George Mock and I'm your guide. Why do you need to understand software pipeline feedback? Well, C7000 depends on software pipelining of your loops to achieve maximum performance. So for an important loop in your code, there are some questions you would need to consider, such as how well does it perform and what changes could you make to have it perform better? And you can answer these questions by understanding the compiler feedback for that loop. This particular video is very example based and I will be showing you things from the command line. I realize not very many people interface with the C7000 compiler from the command line, but it works well for demonstrations like this one. So the first thing to show is this is a source code. It's the same one that was used in the software pipelining introduction video, so I'm not going to go through it in any detail. Pretty much anything would do for this particular video. Any sort of simple loop would work. First thing we're going to do is build it. I have a command in my command history. I reviewed all the options that we're using in previous videos. The important one to discuss here is debug software pipeline is used. This causes the software comment block the compiler generates to be more verbose than usual, and that's going to work well here because we're going to go through all those parts of it. So let's build it. And then I'm going to use Notepad to inspect the assembly code built by the compiler. It's a very simple editor. And this is what it looks like. What you'll want to do is go down to where you see this line. That's the beginning of a long comment block with the information about the software pipeline. When we say software pipeline feedback, we are talking about these lines. It goes on for quite a while. It doesn't end until here. Okay, that's the beginning of some real code. So the first thing we're going to focus on is these lines here. And that's going to be a pattern in this video. I'm going to go to this file, focus on a few lines so that you see them in their greater context, and then when we get back to the PowerPoint slide, you're going to see those lines echoed. But the lines in the PowerPoint slides are from a different loop, so the actual numbers you see, for instance, these 022, you're going to see different numbers in the PowerPoint slides because they're from different loops, and we did it that way to emphasize different points as we move through. So just as long as you don't expect everything to match up, I think it's all going to be fine. When you see the line loop carry dependency bound, what does that mean? It means there's a loop carry path, and that's where one iteration of a loop writes a value that's going to be read in a future iteration of the loop. And this can cause the initiation interval to be higher than might be ideal. Remember, the initiation interval is the metric of the loop, the key metric of the loop that we're trying to keep as small as possible. It's how many cycles are between the beginning of each iteration in the software pipeline. Now, there may not be any loop carry dependency bound, in which case this number is 0. But if there is, then the instructions that are related to that loop carry path are marked with this character, which is called a caret or a circumflex. And so the number is the smallest the II could be because of this loop carried path. Okay, in this particular case, the smallest II this particular loop could be due to this one metric is 2. What might you do about it? It's typically you use the restrict keyword. More details about that, and actually this whole situation will be in the video about the restrict keyword. And that's a pattern you're going to see throughout this video, I'll explain what some line from the software pipeline feedback means, but I won't really say very much about what you do about it because that's usually addressed elsewhere. When you see the line unpartitioned resource bound and some number, what does that mean? Okay, here's what's going on. All the instructions are mapped to functional units, and you remember functional units from the video and the DSP architecture overview. Talked about all these functional units, and the functional units, there's a group of them on the A side and a group of them on the B side. Well, all the instructions are mapped onto functional units, ignoring this partition between A side and B side. And then you ask the question, how many cycles are required by the resource that is used the most, which can seem a bit confusing. So let's walk through an example. So resource is another term for a functional unit. Suppose that in the instructions required for this loop, 4 of them require the D unit. All right, and there are 2 D units available. Okay. So 4 instructions divided by 2 D units means the minimum II this loop could be with regard to this specific situation is 2. Okay, and you can see how you would repeat this for all the instructions in the loop and eventually come up with a number using the, this a computation very similar to this one, and the largest of those numbers is what appears here. Okay, in this particular case, the minimum II that this particular loop can be is 12 cycles. It's got a lot of instructions in it. You could tell if this number is going up to 12, okay? When you see lines that say partition resource bound, similar to these, what does that mean? Okay, so it's similar to the unpartitioned resource bound, but after the instructions are partitioned to either the A side or the B side. One of the things you might remember from the video on the DSP architecture, the B side is mostly vector width instructions, and so if there's some vector width operations that are happening in this loop, those can only occur on the B side, and so on and so forth. There are other examples like that. Many instructions can execute on only A side or only on B side, so that can affect what the resource bound is with regard to partitioning. We show the numbers before and after scheduling. Scheduling is a process of accounting for the fact that things like a multiply instruction, when you issue it, you have to wait 3 cycles before that result is available in the destination register, that sort of thing. That's what scheduling takes care of, and scheduling can add instructions, and so that's why you'll see this number before and after scheduling. Now the video has shifted focus back to the assembly language file that I showed earlier in the video, and I have talked about each of these lines one at a time. This one's also, I already talked about that one as well. What I'm going to talk about next is all of those lines taken together and then how they relate to this line. So the conversation that's coming up is going to relate to all of these lines. What is the significance of these lines taken together? Well, the first initiation interval, II, the first II at which the compiler attempts to software pipeline the loop, is given by the maximum of these 2 numbers in bold. Okay, in this particular example, it's going to be 12. What do these lines represent? Well, we've already established why it started with an II of 12, why the compiler started with an II of 12, and then what happens is multiple attempts are made to software pipeline the loop starting at 12. In this particular case, they fail for various reasons, and eventually the II increments and more attempts follow. In this particular case, a software pipeline schedule is found at an II of 13. Now, we try very hard not to increment the II because the lower the II, the faster the loop, okay? This bit at the end here about iterations in parallel, what does that represent? Well, when you're in the kernel of the loop, how many iterations of the loop are executing at once. In the specific case of 3 iterations, that means before iteration n completes, iterations n+1 and n+2 get started. Back to the assembly language file. Just finished the discussion on these lines. And now I'm going to change to a discussion of these lines. Let's start with resource partition. I'm going to go on down to these lines that are marked bound. Notice throughout this this entire part, there's an A side and a B side, and it's talking about, you know, the instructions on each side of the C7000 DSP. When you see this M and N, L and S, and you'll see it repeated down here in a different way, that's because there are instructions that can execute in multiple units. There are instructions that can execute on M and N, L and S, and so on and so forth. And so, like when you see it here, these are the ones that can execute on M or N or both M and N. Okay. The other thing that's important to notice is that the lines that are called something units, the number represents the number of instructions, whereas the lines that are bound something or another, the number represents the minimum II due to those functional units and the number of instructions that are trying to execute on them. Lastly, note there's an asterisk. That's going to be on the bound line that causes the minimum II of the loop to be, you know, that number. With regard to the lines that show a single functional unit, the number represents the number of instructions that require that specific unit. Instructions that can operate on multiple functional units are not included. With regard to grouped functional units, the number represents the total number of instructions that can execute on all of the listed units. Regarding the cross paths line, suppose you have an instruction that's executing on the B side and it needs to read a register from the A side. It uses a cross path bus to do that. And this number represents the number of instructions that use a cross path bus to move data from the A side to the B side, or vice versa. On the bound lines, the number represents the minimum II at which the loop can software pipeline with regard to those functional units. So let's consider this specific case. Enough instructions execute on .L and .S that require .L1 and .S1 for 3 cycles on the A side, and require .L2 and S2 for 2 cycles on the B side. And that .L, .S, and .LS means instructions that execute only on L, only on S, or on either one. That completes the first of 2 videos which describe the feedback the compiler generates for a software pipeline loop. The second video will pick up right where this one stopped. Before I end this video, I want to give you a couple of references. The first one is to this web address here. It's the home page for the C7000 compiler. If that's too much to type in, I suggest you do a search on C7000 compiler. When I've tried that search with a few different search engines, I always get this web address as the first result. Here's where you can download the compiler, access the manuals, and more. The second reference is to e2e.ti.com. This is where you can go to ask a question about any TI product, including the C7000 compiler. All the compiler-related questions are answered by me. Thank you for watching this video in the series about the C7000 compiler.